Very good morning and welcome you all to this course on smart grids, basics to advanced technologies, and we will be covering today BMS, that is battery management systems. The importance of BMS today is specifically because of the e-mobility and especially for small scale storage applications. Now, without having a BMS, probably the life of those batteries may reduce or deter over a period of time. So, it is expected that the BMS need to perform efficiently, not only balancing those individual cells, but also considering the overall life of those battery can be improved. We will be talking about those important 4 points. One is energy storage technologies, and then we will move to what is BMS, battery management system, and we will also talk about how to monitor and estimate those techniques, and finally the cell balancing, which is the important aspects today. Now, if you look into the evolution of secondary rechargeable cells, now the history is very significant. Now, if you concentrate on a cylindrical type, that is we call C type, and prismatic type, which is P type, and those C and P types of cells, considering its volumetric energy density as well as the energy density considering gravimetric, you can identify that the different type of chemistry or the technology such as lead acid or lithium ion for an example. As you could see, the lithium ion which is leading, that is lithium ion cobalt, lithium ion polymer type, and so and so. So, considering these features in this zone, probably it forces all of us to get into lithium ion rechargeable cells. Those are considered to be very what I can say robust, and the life is also quite reasonable. So, and hence for any mobile applications, especially the electric vehicle segment today needs support through new battery technology, and that is what we are focusing on. BMS along with new technology, new chemistry for battery can help or improve the life of electric vehicles also. Now, a lot of recent advancements in lithium ion batteries, especially solid state electrolyte, silicon based anode, unwraps the opportunity to use particular technology for specific applications. So, let us say any chemistry which may be specific, but depending upon the application, the modularity is going on, keep on changing. Now, here there are a couple of examples you can see in the right side table. Sorry, those letters may not be visible to you so big, but please focus. The right hand side, extreme right hand side, it talks about lithium ion with 3 categories of cobalt, manganese, and phosphate, and then we move to lead acid, the extreme left, and considering those specifications or parameters such as specific energy density, internal resistance, life cycle, fast charge time, overcharge tolerance, self discharge, cell voltage, charge cutoff voltage, discharge cutoff voltage, peak load current, charge temperature, discharge temperature, maintenance requirement, safety requirements, and toxicity, etc. So, these are the variables may decide which chemistry will be chosen for a specific application, and it is very clearly visible from the we talk about energy density. As you could see, it is the cobalt lithium ion which is the best, And if you move to, for an example, let me get into the cell voltage, both the lithium ion, manganese as well as cobalt, both are doing well. And then moving to, for an example, charging temperature, which is quite good, 0 to 45 degrees Celsius, though it is almost similar to other technologies. And maintenance requirement, I wish to focus here this zone, all of you please concentrate. We normally do not prefer to change the battery or the cell frequently, and hence we need to see to that which chemistry or which technology can help us to avoid maintenance or at least minimum maintenance. So, as you could see, for lithium ion, again you could see that maintenance is almost limited, there is no maintenance required, and hence it is very well preferred today. But one important point that I forgot to tell you, though it looks very excellent from the outside, but the cost of lithium ion is extremely good. So, I will certainly recommend lead acid. For example, today if you look into the tri-rickshaws today, or we call it is battery rickshaws or auto rickshaws, they all depend on lead acid batteries, because the cost is so high for lithium ion. So, probably those technologies may not be appropriate for cheap applications. So, for a costly vehicle like 4-wheeler, we can certainly go for lithium ion, but however, for battery rickshaws, lead acid is going to be the best. So, what I wanted to conclude here, we need not be completely biased about the chemistry, which technology is better for me, but one thing is for sure, that depending upon the cost and the type of application, looking at the table, one can certainly choose which technology is going to be the best for us. Now, moving to lithium ion application, considering consumer electronics devices. Consumer electronics devices, lithium ion is almost getting saturated, because almost all the devices have used those technologies. However, for grid energy and industrial energy requirement and e-mobility, that is transportation applications, the market is keep on growing. So, you could see e-cars, e-buses and e-auto bicycles, and then portable energy storage, grid energy, stationary energy storage, renewable energy applications. So, these are the areas actually upcoming. So, I am very sure there are a lot of scopes for us to explore how those lithium ion batteries can be used for those applications, and it is only possible if you can have a better BMS or battery management system. What are those major merits? Why we are so particular or specific for that chemistry related to lithium ion? It has the lightest metal with high potential differences of 4 volt, which are unique characteristics, and commercially available in the market, and the cost of lithium ion is keep on reducing. Now, if the cost of lithium ion is getting reduced, probably there is nothing like this. Today, the only disadvantage with lithium ion with all 3 chemistries, because of the cost limitation, sometime you compromise. However, if it is cheaper, then there is nothing like this. We all have to go for lithium ion, there is no doubt about it, until unless the raw material is not available to us. Now, another interesting part of this lithium ion battery is that it possesses high power density as well as energy density. Okay. So, it can work for a long duration, it can carry out fast charging and discharging. So, these are the merits for this kind of chemistry. One more important part is that it perhaps avoid or do not experience even any stationary losses, that is negligible self discharge rate, which is almost minimum, and it is quite flexible in cell type. So, that the technology can be used, can be manufactured at different magnitude for different application. So, the flexibility starting from a smartphone to a large electric bus, it can be applied. So, that is one of the most advantage or merit for lithium ion. However, there are few limitations, let us do not hesitate to understand those. It requires too much of monitoring and protection, cost of lithium battery is certainly high, that need to be seen, and developing technologies. Every now and then a derivative of lithium ion is popping in the news. So, lithium ion, the chemistries keep on changing. So, you cannot conclude which chemistry for lithium ion is the best, all right. So, aging or degradation effect, that is also need to be seen, and sometime it is prone to overcharge and over discharge. So, that is also, it is quite sensitive to charging and discharging. Then considering all those backgrounds, let us understand why it is important to have a BMS or need of BMS or importance of BMS in energy storage technology. Now, if you integrate or have a BMS, it is something like a battery layer, and top of that we have BMS layer. So, those BMS actually see to that the maximum performance of those battery cells can be extracted because of BMS. So, that is what the beauty is. It reduces the risk of prematurity of the battery, and optimal usage of the battery can be carried out. And heart of all type of energy system today, especially for sensitive batteries like lithium ion, is our BMS, and it enhances the system runtime reliability. As I told you, the performance enhancement, similarly it can enhance system runtime reliability and increase the battery pack efficiency. The efficiency also can be increased because of BMS. So, these are the important advantages. Now, coming back to BMS in detail, the structural thing, it perhaps actually monitor the values of current, voltage and temperature of each cell. The BMS will closely monitor voltages, currents as well as the temperature of each cell, because a cell pack, okay, there will be thousands of cells packed together. So, you look at this big box, but you will find different cells inside. Estimation of key states, that is SOC, state of charge, and SOH using online estimation technique. So, this BMS can help us to through our PC or a laptop, we can easily monitor or estimate those key states of SOC and SOH. Cell module balancing can be carried out both in active or passive balancing techniques. Computing energy and power limit of the pack using SOC and SOH values. We can also calculate not only the state SOC or SOH, but also the state of actually energy and power. Now, if you focus on this diagram, as you could see that this is my cell pack, and you could see that we can keep on monitoring all the observations through PCs, and this kind of pictorial representation, as you could see, one has higher level of energy, the other has lower level of energy. So, how do you balance, okay, so that all cells do possess same kind of same level of power slash energy. Now, how do you monitor? So, it is quite important. So, we will talk about LTC 6803 for detailed understanding. The BMS requires a sensing IC for monitoring. The parameters that can be sensed directly from a battery cell are current through the circuit, terminal voltages and ambient temperatures. As I told you, it is about current, voltage and temperature. Now, you could see the LTC 6803 chip which is used for 12 cell monitoring, and this is the internal schematic diagrams, and we can also use this for multiple applications. So, this is where it is a small laboratory arrangement where you could see cell number 1, 2, 3 are being used. That means LTC 6803 is being used for 3 cell monitoring. Now, there are different techniques, okay, multiple techniques available for SOC estimation, and many times it was a question for all of us how to perfectly predict SOC. Many times you might have seen that your laptop that may show you the SOC is let us say 50%, and next few minutes you see it is 20 and it really discharge very quickly, or sometime it almost surprise you with the battery status that is being shown to you through a diagram. The main reason, even in the case of mobiles, okay, so the SOC technology, those are used for understanding the state of charge of any battery. Those algorithms are not very efficient, I will say, or depending upon the application or cost reduction, a cheaper algorithms are being used or an approximate algorithms are being used for SOC, but we cannot afford to do it in case of an electric vehicle. Okay. So, if you look at the battery and you see that the BMS speaks you or display that it can go up to 25 kilometers with SOC of 15%, then probably it has to be absolutely correct. So, we cannot compromise on that. So, let us focus on what are those characterization of SOC estimation methods. So, there are 5 different characterizations. So, first one is conventional methods, and we will move to adaptive filter method, then learning algorithms, nonlinear observers, and then advanced algorithms. Now, within each conventional method there are different categories. One is open circuit voltage method, then you have Coulomb counting, then electrochemical impedance spectroscopy, and model based SOC estimation. Now, those who are doing research or interested to explore, this is a very, very wonderful area. So, in our laboratory at IIT Roorkee, we have tried to do something, and it is really we are keep on exploring, because we have very limited research background or the references available across the globe. So, I think this is a wonderful area for the new researchers and scholars to explore, looking into the future e-mobility in market. Now, adaptive filter methods, you can once again explore actually Kalman filter, extended Kalman filter, H filter, sigma point Kalman filter. Then moving to learning algorithms, we can explore neural networks, fuzzy logic, genetic algorithm, support vector machine, and many more. Now, nonlinear observer, where we focus on sliding mode observer, nonlinear observer, and the advanced algorithm where we focus on deep learning techniques, machine learning techniques, or sometime it is hybrid of multiple techniques. So, this is a wonderful area. So, I expect actually all of us to spend some time and try to understand the whole SOC estimation technique. And now, let us focus on each method, how each method kind of depending upon the applications, you need to choose which SOC algorithm need to be used. Once you understand the limitation and merits of each algorithm, then probably you will be able to deploy in real time. Now, moving to conventional method, as you could see, there are a couple of major limitations, and they are not suitable for online, and it highly depends on the accuracy of the model, this challenge, and also the aging and temperature issues become a challenge. Now, whereas the merits are easy implementation, low power consumption, high accuracy, and quite easy to understand. So, for conventional method, so there are few merits as well as limitations, and moving to adaptive filter, as you could see again it is quite complex in computation, large computational cost, and hence it can be avoided, unfit for large noise measurement, that is also equally important. So, we normally avoid. However, the accuracy is quite high, excellent filtering effect, insensitive to initial state of charge, and high robustness. Okay. So, to me adaptive filter is certainly a good option. Now, the learning algorithms which are challenging, where we can say the merits of learning algorithms as well as limitations. The limitations are requires a large amount of training data, and which is a risky analysis, requires large memory units, costly processing units not prepared, and certainly it is a time consuming process. So, for real time application it become a challenge, but they are quite independent, great accuracy, it is rule based inference and nonlinear mapping ability. Now, moving to the fourth method, which is nonlinear observer method, and it is quite inaccurate, and it is difficult to find proper gain metrics and insufficient stability, and hence it is also not preferred when stability become an issue. But it is quite robust and powerful tracking performance, and hence preferred, and the excellent nonlinear processing capability, and hence it is also acceptable. Now, moving to hybrid techniques, it requires longer time duration and high complex computation. These are the two challenges, but the only interesting part here, it poses high precision, reliable and most effective. So, everything is in front of you, the measure benefits and limitation of all those 5 characterization of SOC estimation methods, and based on those characterization of SOC estimation methods, we can choose one of them depending upon your application and considering the limitations in mind. Okay. And now we will move to the equivalent circuit model, which is we have discussed yesterday on the previous units perhaps, where equivalent circuit models, as you could see, that it is simple. We have a voltage model, then you have a series resistance, and then resistance and capacitance in parallel. So, the basic voltage equation, I mean, that is your ut, the voltage available to me here, all right, is nothing but my uoc minus the drop due to RL and the RC shunt circuit, that is IL RI as well as UD. Now, if you can write the expression, because UD is nothing but the voltage across this terminal, you can write the differential equations. So, dUd upon dt, which is minus 1 upon CdR dUd plus 1 upon CdIL, and if you solve this equation for UdT, you will end up with this equation number 3, which is e to power minus 1 upon CdR d t minus t naught ud t naught plus e to the power minus 1 upon CdR dt minus t naught 1 upon CD IL tau d tau, where the tau is nothing but my RD and CD, please remember. All right. And further we can rewrite the UdK, the voltage at any given point of time or state, is given by e to power minus delta t tau ud k minus 1, the previous state, plus 1 minus e to power minus delta t upon tau I L k R d. So, the equation number 1, 2, 3, 4, they are the basic equation related to a battery based on its physical representation. Now, once you calculate the open circuit voltage of this arrangement, you can plot a graph between open circuit voltage, that is OCV, and SOC, state of charge, and you could see that this is my SOC starting from 0%, 20, 40, 60, 80 and 100, and you can have open circuit voltage which is again varying from 3.5 to 4 for example. So, this is the characteristic you could get it now. So, once I know the value of OCV, open circuit voltage, then easily I can calculate the state of charge. So, once the OCV of any arrangement is known to me, then probably I can capture the state of charge of this battery. Now, let us get into the practical look and implementation part of typical module and pack control of BMS. You all may be knowing these are wonderful cells, as you could see. Okay, you might have seen and you can visualize it. So, these are the cells, but they are not like your normal battery cell, though physically they look like this, but they are different. So, these are Tesla cells actually, and then actually you can stack them horizontally as well as both in x and y axis. So, it is a 2-dimensional pack, and as you could see that this is my actually BMS part. Okay. So, you have a box attached with a BMS part. So, you put each and every cell. So, this is cell number 1, 2, 3, 4, 1, 2, 3, 4, 5. So, 5 by 4 there are 20 cells, then you have a thin layer of BMS. So, that is the balancing modular controller with cell balancing circuit, and finally, you will see the battery pack will look like this. So, outside it will look like simply a box which has certain input output terminals, and there is a chip for my balancing circuit, and this is completely my battery pack. So, the practical battery box look like this. If you open it up, then you can see all those circuits and the cells, many cells inside that. So, indirectly you have battery module controller, and then you have battery pack controller, and this is the overall packing of the system. Now, what is the reason and why we go for actually cell balancing? That is an important question. Now, what exactly happens that over a period of time, each cell actually start discharging, and given a point of time actually they also observe energy and charge too. Now, if I take two batteries within a overall pack of let us say 100 batteries, it is not necessary that each of them have equally discharged and equally charged, though we expect that to happen. But due to the arrangements, probably it is not necessarily true always. So, you have to see to that through some mechanism at any given point of time or any time t, all the batteries do possess the same level of energy. Now, focusing on SOC and SOH, now there are few challenges with SOC. Leakage and self discharge current, that may affect my SOC, Coulombic efficiency, performance and operation, and uneven temperature. The as in when you use any battery cell pack for any application, even for a mobile, you can feel that heat. And when you move to SOH, internal resistance issue, self discharge issue, static electrolytic interface issues, and hence performance and operation. Now, if balancing is not implemented, the weak cells or less capacity cells tend to discharge faster than the other. If you do not have any balancing mechanism, then the weak cells will discharge very quickly. If this continue to happen, out of n number of cells, let us say half of them actually completely discharge and half of them have not completely discharged. So, if it continue to happen, the less capacity cell will gradually premature than others. If that happens, then slowly the deterioration begins. Imagine a case where less capacity cell and fully capacity cell connected to a load, it will neither discharge nor charge. The biggest challenge. So, if you have a load and you have two cells, one is 20% capacity, the other is actually 100% capacity, and if they are connected to my load, I think there will be a bigger issue, neither they will be able to properly charge or nor they discharge properly, and hence a balancing is required. So, this need to be reduced to 80% and this need to be improved to 80%, so that both the batteries possess the same level of energy and hence the proper charging and discharging can happen. You can also see in this diagram. So, this is your discharge which is 30% and the maximum charging could be 90%, and you could see some cells do have 90% and some of them do have less than 90, and this is an issue and it is necessary for cell balancing. Now, once again when you move to cell balancing methods, there are different cell balancing methods. We have passive methods and active methods, and different algorithms are used for cell balancing. Now, let us focus on passive and active balancing. So, first of all let us understand what is passive balancing. Now, passive balancing uses a resistor connecting across the cell which bleeds the high charge battery cell voltage. However, in case of active balancing exchanges the energy between the higher capacity to lower capacity cell without any dissipation. So, active balance mainly focus on your energy, however, the passive balancing focus on voltages. Okay. So, these are the different topologies researchers are keep on working on, and I mean but the active balancing topologies we have many types, there are 4 types, and passive balancing you have 2 types, and perhaps you can choose any one of them. Over a period of time the structure, the architect, the topologies keep on changing, and in the balancing one we talk about shunt resistor, switched shunt resistor topology, single switched capacitor, multiple switched capacitor, switched transformer and share transformer topologies. So, these are topologies, they have been kind of evolving over a period of time, and the performance are considered to be better in recent time. Now, what is happening between 2 adjacent cells? All of you please focus. Now, in case of a cell balancing topology, what we can do so that the voltage across each cell become fixed or constant, and the energy also remains same in case of passive as well as active for voltage applications. Now, this is one of the structure where we see to that this kind of arrangements where the voltages for across each cell are maintained constant, and this is the kind of topology are being used to make sure the voltage across each cell remain same. And this kind of balancing a single tiered switch capacitor topology, double tiered switch capacitor, the second one B, and then chain structure switched one, and then 2 phase switch capacitor, and we move to forward, and then we move to flyback multi winding transformer topology. So, these are n number of algorithms and topologies are available to us, and you have to choose one for better applications. Now, in this actually perhaps there is also, instead of moving in case of adjacent cell to cell, this is one of the concept, then any cell to any cell, another technique, and the third one is direct cell to cell. Okay, this is quite important. So, this is what the complete topology, and you can perhaps spend more time to understand in detail about each model if you are really focusing on getting into a BTech project or master's thesis or PhD applications. Now, the first one, the first structure, which is a flying capacitor, bidirectional flyback converter, quasi resonant LC converter with the boost converters, and LC resonant circuits, and finally single inductor switching circuits. So, I think this course in which we are trying to bring all the background history of BMS, those are available, and for the benefit of students and the learners, we have captured all the resource materials available to us, and probably it is high time for you to get into details and try to understand more about it. Now, a ideal cell balancer, which basically which is a simple circuit, which must possess, we can say it is ideal cell balancing if it is fast equalization, high efficiency, optimal size of passive elements, less voltage stress on batteries, good balancing speed, real world implementation is possible, control simplicity, modularity, less sensor requirements, and apply for static and dynamic balancing, and finally, it has to be quite economical. I think there is a huge list of references for you, and probably I have tried my best to capture almost all the references for your best use, and I am confident that you will be able to understand more detailed BMS applications in energy storage systems. So, with this, thank you very much, and looking forward to see you next lecture. Thank you and patience listening. Bye bye.